All right, guys. I'm going to show you how we do the taxation because I see some questions on Piazza. I hope this would help. Let me try share my screen. All right. So link analysis is very useful and it's actually very simple. What we want to look for is we have some graph. And based on the graph, we want to be able to say some links are more important than others. Sorry, some nodes are more important than other nodes, right? And here we are actually looking at a directed graph. So let me try to make this more useful. Okay, so this is our input, and we are looking at all this graph structure to help us decide which node is more important. So we begin from looking at the transition matrix, because the transition matrix has all the information we need about how each node connects to other nodes in the graph, right? So, and we also cover something called stationary distribution. If you have a transition matrix and a strongly connected graph, you take rank vector, multiply your rank vector by your transition matrix. Eventually, you get exactly the same rank vector, right? So this two is the same one, okay? And this graph is actually not strongly connected, so let's make it more strongly connected. So now we have this basic definition of the problem. One thing that applying this link analysis to a real graph is very often your graph is not strongly connected. So what do we do? A very simple solution is we do teleporting or taxation. So from each node, we say this node will go to this one, to this one, to this one, with some probability. Okay, so we do this for every node, not just this one node I'm showing here. You need to do this for every other node, okay, etc. So how does this change our transition matrix? So if we look at our new transition matrix and prime, it will be some damping factor, let's use 0.8 times your original transition matrix plus a teleport. Let's call this teleporting matrix MT. Okay, so we already know this. This one is the same. So what is your teleporting matrix? Teleporting matrix is a very simple matrix. Oh. It will have the same dimension as your transition matrix. So for example, let's say this one is n by n, assuming you have n nodes. This one will be what? Also n by n, right? So if you look at the n by n matrix, what would be the values of each row and columns? In this n by n matrix, because we are saying this is teleporting from one node, you have equal probability to go to any other node. So every element here is 1 over n. This tells you what? This tells you from this node, it has 1 over n probability to stay at the same node, or 1 over n probability to go to all other nodes, right? So if we rewrite this, take your 0.8 and 0.2, you have empty. Okay. So one question was asked is, do we do this? Do we do the calculation? This because now we don't have m, we have m prime. So now you do m prime times v equal to v, right? So this will be eventually be your rank vector. So when we are calculating this, either you do power iteration or find the eigenvector and eigenvalues. Which matrix do we use? Do we separate m and mt, or we just use m prime? So in practice, you just use m prime because it's easier. You don't have to do this 0.8 and 0.2 all the time. But on the slide and in the textbook, to show you how the text affect your rank, we separate them. So it's very simple. But let's look at how we would be able to separate them. If you look at your slides, let me see which one. If you look at your slide 74 and 75, and all other slides that have not separate your M and MT. Let's say you look at your 74. Okay, so it says you have V prime equal to 0.8 times the original transition matrix times V plus 0.2 times this 1 over n vector. Okay, so how does this work? We haven't really seen this before, but it's very simple. It's this. So if we take your m prime, let's say your m prime v would be 0.8 m, right? We're looking at this. V, right, times plus 0.2 mt times v. Okay, so if you compare these two, can you start to see similarity? First, this one is exactly this one, right? How about this two? You do have 0.2 and 0.2. So what we want to show is your MT times V would equal to this. What is your MT then? Remember, we have your MT here, right? So your MT is something like this. If you times the vector V, V has all these random numbers we don't know. At the beginning, first, when you initialize it, it's something like this, right? But it doesn't have to be like this. It can be anything else. But there's a constraint on your V. So what is that constraint? That's every component in V. Let's say the first component is x0, the second component is x1 plus xn, because you have n components in your V vector, will need to be 1, right? So if we look at this one, this is n by n times m by 1. You will have something like your result will be n times 1. So it's a vector, right? Only one column. If we think about this one, okay, the first element in your new vector, this new element is the dot product between this and this, right? So this is this. So if we only look at your first element, it's n over 1 times x0 plus n over 1 times x1 till n minus 1 times, sorry, 1 over n times xn. And if you take 1 over n out, you have x0 plus x1 plus xn, and this is what? This is 1, right? So then this leaves you 1 over n. So each element here will be 1 over n, 1 over n, and 1 over n. So it's just to show you that you can derive this from this. Okay, are we good? So this means the text here, your gain from the text never change. Doesn't really matter what your V is, as long as they all sum up to 1. Okay. But when you are looking at the gain and losses for your spider, for the spider and for the dead end, why are we looking at this one and this one separately? The answer is that every time when you have spider or when you have your dead end, this part is very interesting. For example, if you have dead ends, you have a lot of zeros, and you will be able to see how this V, the ranking of the V, start to get smaller. The summation of all the ranks in V start to get smaller, and when you have spider net, you can actually look at the rank here in the transition matrix to see how the spider structure in your graph would affect your ranks. So that's it. That's very simple. For your other slides, if you look at your slides 75, 76, and all the tables in 77, 78, it's just a way to help you how you would be able to calculate the loss and calculate the gain due to the teleporting. But if you understand how the matrix works here, you should be fine. And you need to know how you will be able to generate or to calculate the values in all these taxation tables. All right, that's it for today. I will see you tonight.